Okay, so good morning, guys. So today we'd like to talk about calculus, calculus BC for the trigonometric substitution for the integration. So here's the list of the trigonometric substitution that we can use to integrate any kind of radical, any kind of complicated radical. So there's a certain kind of pattern that I need to recognize in order to apply the trigonometric substitution. So with the identity, so let's go through the table from right to left. So from pre-cal, as you do remember that the Pythagorean identity, so we do have 1 minus sine square of theta, so that equals cosine square of theta. So anytime that you see something that is considered square root of a squared minus x squared, so we're using the pattern as substitution with x equals a sine theta. So x equals a sine theta, it's kind of like a polar equation, or the rectangular form to the polar equation substitution. So for the polar, I'm going to have another video for that in the future. So negative power 2 to power 2, again, that's the restricted range of inverse of sine. And for the pattern of square root of a squared plus x squared, as you can see that a squared plus x squared, it's kind of like a Pythagorean theorem. So for that one, so we want to set up x equals a tangent of theta. And again, inverse of tangent, the restricted range of inverse of tangent would be from negative power 2 to power 2. And that's something you guys should know from pre-calc, the restricted range. And then for the other one, it's x squared minus a squared, so the variable goes first. So that one, we're using x equals a secant of theta. So for the restricted range for that one, so it's from 0 to pi over 2, and then theta from pi to 3 pi over 2. So now we'll deal with some of the example in just a minute. So let's start it off with that. Evaluate square root of 9 minus x squared over x squared dx. So this one is just showing one of the pattern as a squared minus x squared. So we're using the first one, the first category, the first scenario. So let x equals 3 sine theta. So where theta is right between negative power 2 to power 2. So that means dx would be considered 3 cosine of theta, d theta. So by using that substitution, so we got 9 minus 9 sine square of theta. So by using the identity, so we took out 9, so we got 1 minus sine square of theta, so which is considered cosine square of theta. So taking square root of this, so we do have 3 absolute value of cosine of theta, which is the same as 3 cosine of theta. And then by plugging that to the integral, so we do have 3 cosine of theta. And then x squared can be replaced by 9 sine square of theta. Once again, x is considered 3 sine theta, so x squared, so it's 9 sine square of theta. And then dx, taking the derivative of 3 sine theta, so we got 3 cosine theta, d theta. So before you integrate it, always you want to use any trig identity or any things that can be simplified, you just try to reduce it. So we got cosine theta, so that's cosine square of theta over sine square of theta, then that's cotangent square of theta. And so far, there's no such formula for integrals of cosine square of theta. So we're using the identities, which is considered cosecant square of theta minus 1. Again, that's just the Pythagorean identity right here. And then integrals of cosecant square of theta, which is considered negative cotangent of theta. Integrals of negative 1 is negative theta. And then plus constant c, because this one is the indefinite integral. And then once we come up with that, so you'll get the integral. But the things that we're not done here yet, this one, everything is written in terms of theta. But don't forget to plug in this one back to x. Okay, so we'll see that in a minute. So the definite integral, indefinite integral, so we must return the original variable x. So this can be done either of those two ways. So we can use that sine of theta as x over 3. So try to draw the triangle. So we do have theta. So x over 3, which is considered opposite over hypotenuse. And then for the adjacent, which is considered square root of 9 minus x squared by using the Pythagorean theorem. And then it's all about the replacement. Okay, so once we find that, so we just replace that by using square root of 9 minus x squared over x squared. Again, it's adjacent over opposite. So back to the diagram that we have. So it's adjacent over opposite for negative cotangent. And then the other part, theta, is just the inverse of sine of x over 3. Again, x over 3, that's just the ratios. It's opposite over hypotenuse, and then plus constant c. So here's another problem by using the trigonometric substitution. So we do know that it's the equation of ellipse with the center of 0, 0, a squared, b squared. So we try to solve for y in terms of x. So you end up with plus minus b over a square root of a squared minus x squared. And as you may notice that this one is bounded from 0 to a, and then for the vertical axis, it bounded from 0 to b. So that means we're just taking 1/4 of the area of this first quadrant, the area of the whole thing. So it's 1/4 of the area. So once you integrate it, we do have integral from 0 to a, b over a, square root of a squared minus x squared. So b and a, those are just the arbitrary constants, so we can just separate them out. Again, you see the pattern here is considered constant squared minus x squared. So again, we're using x equals a sine theta. So dx is a cosine theta d theta. So it's quite similar to the problem that we did for the first one. And then set up the boundary. So when x equals 0, sine of theta equals 0. So that means theta must be 0, taking the inverse. Because this one we try to integrate it in terms of theta, not x. And then for x equals a, sine of theta equals 1. So that means theta must be pi over 2. And then we just set up the integral, the integrand, by using theta. So a squared minus a squared sine squared theta using the trig identity. So we do have a squared cosine squared of theta, which is considered a absolute value of cosine of theta, a cosine theta. And we try to do the integration by using the identity. Again, cosine squared of theta cannot be integrated. It's a power. So it's a high power, so that means we're using the power reducing formula. So a lot of people that probably forget about the power reducing formula from pre-calc. It's considered 1 plus cosine of 2 theta over 2. And then for AB, just a constant, we can just leave that outside. So integrate it. So we do have theta plus 1/2 sine of 2 theta. And then the boundary is from 0 to pi over 2. And then by using fundamental theorem of calculus, part 1, so by plugging f of b, f of a, and then we just solve for the area. So we got pi AB. And you may notice that the area of the ellipse is also considered pi AB. So A, which is the distance of the major axis, and B is the distance of the minor axis, if that's a horizontal ellipse. If that's the vertical ellipse, that would be the other way around. So pi is just the constant. It's a proportional constant. So now we'll take a look at more example in just a second. So here's another one. So as you can see that it's a pattern of the second scenario, x squared plus 4. So we do use x equals 2 tangent theta. And then by taking derivatives, so dx is 2 secant square of theta. Again, it's all about the bunch of replacement and substitution. So we do have 4 times the quantity of tangent square of theta plus 1. So 4 secant square of theta. So square root of this, so we do have 2 secant of theta. And then by plugging back to the integrand, so we do have 2 secant square of theta, d theta, and then 4 times tangent square of theta, 2 secant of theta.
Dalia Harner, please come to the front office. Dalia Harner, please come to the front office.
And sorry for the interruption, it's a lunchtime at this moment. So we do have 1/4 integrals of secant of theta over tangent square of theta, d theta. And then by using the trig identity, so we do have 1 over cosine theta, cosine square of theta over sine square of theta. Again, we try to simplify it all the way down to the simplest form before we try to integrate it. So we do have cosine of theta over sine square of theta. And then this one we can use the u substitution. So u, that would be sine of theta. And then du would be cosine of theta d theta. And then by using that, du over u squared, integrate it. So we do have 1/4 negative 1 over u plus c. And then unpack with the substitution, we do have negative 1 over 4 sine of theta plus c. So this one can be written as negative cosecant of theta over 4. Again, it's all about the reciprocal identity of sine of theta. So one more thing that we need to do is by replugging everything back in terms of x. So we use to figure it out to determine what that is. So cosecant of theta is considered square root of x squared plus 4 over x. That's what I showed earlier. So that means this one would be considered the hypotenuse, and then x would be the opposite, and then 2, which is the adjacent, by using the Pythagorean theorem. And then simply just rewrite it. So cosecant, then that would be just square root of x squared plus 4 over x. And then negative 1, 4 is just a constant. We just want to carry that over, plus c. So here's another example you might want to try. Again, it's using the pattern of x equals 2 tangent theta. And the reason why that I know that a is 2, because that it shows the pattern of x squared plus a squared. So a squared, that means 4. And then a would be considered 2. And then we just follow through the previous idea, so we end up with something like this. Okay, so thank you for watching the video today. And always you can just either fast forward or you can rewind it. You know, anything that you're getting stuck with the example that we just went over today. Thank you for watching.